Welcome to Graphs of Polynomial Functions Part 1, where we look at what happens to functions away from the origin. So we're going to start with reviewing power functions. Power functions are in the form f of x equals a times x to the n, where a is just any real number not equal to 0, and here is an integer that's greater than or equal to 1. If n is equal to 1, then we get a linear function, so that's not very exciting. So we will be focusing on power functions where n is 2 or larger. So we're going to start with an exploration. We're going to graph three functions on the same set of axes. I have these functions written in terms of x and y instead of function notation because I'm going to graph them on my graphing calculator. So I'm graphing in y1, x to the third, in y2, x to the fifth, and in y3, x to the seventh. So I have my graphing calculator here. Just slide this over so we can see our functions. And in y1, I'll go ahead and graph x to the third power. In y2, x to the fifth power. And in y3, x to the seventh power. So all of the exponents are odd. So that's x to the third, x to the fifth, and x to the seventh. So it's kind of hard to see, so I'm going to zoom in a little bit. I'm going to choose zoom 4. There's x to the third, x to the fifth, and x to the seventh. So you can see they're very, very similar in shape, and even as we get close to the origin, they're very, very close together. The values of the functions are very close. But overall, we want to just focus right now on the shape of the function, and the shape of all three of these functions is exactly the same. It goes up and to the right, down and to the left. It's symmetric to the origin, so if we turn this graph upside down, it will look exactly the same as it does right side up. Notice again that we have all odd power functions here. Okay, in our next exploration, we're going to do something similar, except we will graph x squared, x to the fourth, and x to the sixth. So we're looking at even-powered functions. So let me go back to my y equals. I could clear everything out, but I might as well just type over what I have in here. So the first one will be x to the second. Second one will be x to the fourth. And then the third one will be x to the sixth. I'm going to go back to the standard window before I hit graph. There's x squared, x to the fourth, and x to the sixth. So you see that they got a little bit skinnier as the exponent got larger. Even if we zoom in, now let's go to our zoom 4, x squared, x to the fourth, x to the sixth. You can also see that as the exponent gets larger, it starts to flatten out near the origin as well. And we did get that effect with the last example. It's just a little bit harder to see. So it was these are a little skinnier as far as vertical width here, or I guess a horizontal width, but they flatten out near the origin as the power of x gets higher. But again, focusing on the overall shape, they're very similar in shape. We have a parabolic shape for each of them. It goes up and to the right and up and to the left. Now, for the examples we just saw, the leading coefficient a was 1. But we know that as we change that leading coefficient, it's going to have an effect on the graph because we've already talked about transformations. So if a is positive, and we're talking not equal to 1 here, we're going to have a vertical stretch or compression. If it's bigger than 1 and positive, we'll have a vertical stretch. If it's between 0 and 1, we'll have a vertical compression. Now, if a happens to be negative, we are still going to get the vertical stretch or compression depending on if the absolute value of a is greater than 1 or less than 1. But because of the fact that because of the fact that it's negative, we're actually also going to get a reflection over the x-axis. So there are two transformations that happen when a is a negative value. All right, so now if we take these power functions and we add them together, so we can add as many of these power functions as we want, we get a general polynomial function that has more than one term. So this is a general definition for a polynomial function. Remember, a polynomial just means many terms. So what we have here are many terms. The number of terms can vary. It is a finite number of terms. So polynomials have a first term and a last term. It does not go on forever. And let's just talk about this definition a little bit. So you see this first term just looks just like a power function. The only difference here is that we gave a little subscript n for the coefficient. And that's just so we know that the coefficient here matches up with the term with the power of n. So you see in the next term it's also a power function, but the subscript here is n minus 1, and that matches with the exponent here. The subscripts are just indicators, just names for us to match up the coefficient with the power of x. It's not a value that you actually see in the function. And this will continue to go down. If we have our terms in order, we'll eventually get to the x to the first term and to the constant term. Of course, any of these terms can be deleted, so all of these a values are just real numbers. The only exception is that the first value here can't be 0. The n's are all integers that are greater than or equal to 1. Now, if we graph these polynomial functions, we have the following characteristics. These graphs are what we call continuous, which right now for us means that it has no breaks, no gaps, or no holes. There's a calculus definition for continuous, but we're not quite up to that level yet. We also consider these graphs to be smooth. Again, that's a calculus term, but for us that means that there are no corners or no cusps in the graph. The domain for all polynomial functions is negative infinity to positive infinity, and that's because we have no restrictions on what we can plug in for x. There are no x's in the denominator to worry about, there are no x's in a square root or fourth root to worry about as well. Now the highest exponent on the variable, in this case, in this general form would be n. That is what we call the degree of a polynomial function. Since we're looking at a function in one variable x, we can just take the highest exponent on the variable to be the degree. The leading term is the term that contains the highest exponent. So if our terms are written in descending order by degree, it would be the first term. That's why we usually call it the leading term. Now there is some other implications of that leading term, and we'll see what that is in a moment. Right now we're just going to talk about something called end behavior. So end behavior describes what's happening to the function as x goes to positive infinity or negative infinity. And again, this is as we go away from the origin. So x is getting really, really, really large in the positive direction and really, 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 really small in the negative direction, getting really far away from 0. Now the claim is that the leading term of a polynomial function determines the end behavior. That's all we need to look at to decide what is going to happen to this function as x goes to positive infinity and to negative infinity. So we're going to look at two sets of functions, and we're going to look at their graphs. First, we're going to graph y equals 3x to the 5th minus 5x to the 3rd plus 2x, and then we're just going to graph the leading term of that and make a comparison. So back to my graphing calculator, turn it on, clear out what's in here from before, and I'm going ahead and I'm typing in my first function, which is 3x to the 5th minus 5x to the 3rd, and let me see what the rest of it is, plus 2x. Just slide this back over. And then in y2, I'm just going to graph the leading term 3x to the 5th. I'm going to fuss with my window here, so I'm still in Zoom 4 right now. And I see I have my two functions. Let me change my window here. I'm going to change my x min to -1, x max to +1, and the same for my y min and y max, -1 to +1. Then I'm going to go ahead and graph again. So this first function is the one with many terms, and the second function is just the first term, 3x to the 5th. Close to the origin, they look very, very different, right? Right now we're really zoomed in. I'm going from -1 to 1, from -1 to 1 along the y as well. Let me start to adjust my window. So now I'm going to change my x min and max from -2 to 2. And same with my y min and y max, -2 to 2. So I'll be zooming out a little bit further. There's that first function, 3 terms. And here comes the next function, which is that leading term. All right, again, close to the origin, they don't look alike at all. But as we move away from the origin, they're starting to do the same thing, going up and to the right, down and to the left. Let's continue to change the window. I'm going to go from -3 to 3 on my x min and max. And then I'm really going to adjust my y min and max. So y min -50, y max +50. Because this is moving very slowly in terms of the x values, it's moving very slowly away from the origin. So there's that first function. Notice all those bumps seem to have disappeared because I'm zoomed out so far. And there's the second function as well. And again, as we go or make our window larger, zoom out, these functions look almost the same. I mean, they're going in the same direction. We don't see those little bumps anymore near the origin. They're a little bit different though, so let's go ahead and change our window one more time. The x min and max, I'm going to go from -10 to 10. And the y min and max, again, I'm going to adjust drastically here. So we're going -10,000 to +10,000. Just count my zeros here. Yeah. All right, so let's go ahead and graph. And there's the first function. Again, that's the one that has 3 terms. And the second function is just the leading term. And you see they practically trace one another. So essentially, as we zoom out, or as we get further and further away from the origin, these functions are just going to look the same. So we're going to do the same thing with the second set here, our y1 and our y2. So let me go ahead and graph those. Just to save time, I'll graph those and then come right back to you. Okay, so I've entered both of my functions. I've also changed my window, so my x min and max are going from -5 to 5, my y min and max -20 to 20. So let's go ahead and hit graph, and we see that, again, close to the origin, these functions are very, very different. Let me adjust my window one more time. I'm going to change my x min to -10, x max to +10, y min to -20. We'll keep that at -20, but my y max I'm going to change to 300. So there's the first function. I don't see those little bumps as much. And then just the leading term, I see that they start to really match up. And as I adjust my window, these are really going to coincide as I make my y max much bigger. Okay, so what we get is the following summaries. So this is what we have when n is even. So we have the positive case for A and the negative case for A. So I urge you to take a pause here and just read through these pictures and absorb what's happening. Also read what's happening at the bottom here. And then for the other case when n is odd, we have these pictures. And again, I urge you to pause this video and really look at these pictures, see what's happening, and really focus on what's happening as x goes to infinity and negative infinity. All right, thanks for watching this video.